Okay, so let's get started. So before we start, I have to confess that I made a really terrible mistake on the calculations yesterday, which no one has come and complained to me, so I guess no one noticed. Yeah. So in the words of an infinitely better relativist than myself, I lied to you. Okay, I lied very badly. So what I did was I was giving you an argument of uniqueness for a nonlinear elliptic equation. And the example that I had, that I wrote down, was this one. And I did a proof assuming that there was a positive maximum of the difference between two solutions, and this went through. And then I said, well, I have yet to do the negative minimum, and that works out fine. In fact, that doesn't work out fine because the proof does not go through for this example. The example I had meant to write down was this one. And for this one, the proof goes through fine. And I actually have no idea why I wrote down phi squared, because even my notes said phi cubed, and everywhere on the notes it said phi cubed, and for some reason I started with phi squared and then just carried on. And actually, if I had tried to complete the proof, bad things would have happened, and then we would have seen that it doesn't work. So in fact, when you do these checks of uniqueness, you definitely need to complete the proof all the way through. So actually, this is the example for which there are unique solutions, and the uniqueness proof works. And this is the example that you'll be looking at in the exercises. Okay, so. But today Harold is here in the audience, so if I make any stupid mistakes again, then he will correct me.
And also, while we were actually writing the boundary conditions for that linearized problem,
yes,
I was not able to understand how the delta of that thing is also how it is satisfying the same boundary conditions.
Why the delta satisfies the same boundary conditions? So if I write. So if we now consider the correct problem, if we write the solution as some guess plus a correction, right? If this, so that our boundary conditions were that the derivative is 0 at the origin, and the function is equal to 1 at the rightmost boundary. If I choose a guess that satisfies these boundary conditions, my first guess. So we let phi bar equal 1. Right? That is a perfectly fine guess that satisfies these boundary conditions. Right? The derivative is 0 at the origin. It's 0 everywhere. It's constant, and the value is 1 at the rightmost end. So that's a perfectly fine guess. So if I start with this guess, then the boundary conditions on I know the boundary conditions on phi, and I know what phi bar is, so I can immediately see what the boundary conditions must be on delta phi, and I again have the delta phi at 0 prime has to be 0. The derivative has to be 0 still. All right? I mean simply that phi prime is phi bar prime plus delta phi prime. Phi bar is a constant, so that's 0. So if this is 0, then this must be 0. Okay, so the boundary condition on this correction function is that the derivative is 0 at the origin, and this function, the phi bar, is already 1 at the rightmost boundary, so the boundary condition on this correction function is simply 0, because we clearly need a 0 correction to phi bar to get the boundary condition satisfied at the rightmost boundary.
These are the boundary conditions that will appear in the first step of our calculation. But as we are to repeat in every step we will be getting the new phi bar.
Right, so you perform one iteration, and you will now have a new phi bar, but it will also, of course, the new phi bar will also, of course, be 1 at the rightmost boundary, because the original function was 1 and the correction is 0, so the new function is also 1 there. the derivative was originally 0. The correction has a derivative of 0 at this boundary. And so again, the derivative of phi bar will be 0. So this is now set up in a way that for each iteration you have the same boundary condition. If you keep running each iteration with this boundary conditions, it will work. Okay, so I now want to move on to away from numerical techniques and for general elliptic equations and the discussion of elliptic equations, and actually start talking about numerical relativity. And today I'm going to talk about the Schwarzschild solution, and there are some interesting things that happen with the Schwarzschild solution, which I think also illustrate some of the ideas that Thomas presented last week in doing the 3 plus 1 decomposition. And this also motivates a 1D elliptic equation, which you can look at in the exercises, which is basically combines all the ideas that we've looked at so far. So it's a nonlinear equation, so you have to linearize it. It has it's a spherically symmetric equation, so it's in some sense similar to the radial equation that you looked at. So I think it's a good example. And then tomorrow we'll talk about binary black hole data. Okay, so if we look at the Schwarzschild space-time. Okay, so this is the first part here. I think will be a recap on what Thomas did. But if you take the standard Schwarzschild solution, all right. So if we write down the solution. Okay, if we were to look at this and we think, okay, this would be the ideal test case for some numerical. If we want to do numerical relativity on black holes, the ideal test case presumably would be Schwarzschild, because we know the solution. It's a nice static solution. Presumably we could code this up and run it, and essentially nothing would happen. We would just keep our nice solution. Well, there's a problem. There's many problems here with the solution in this form. Notably, of course, that as r goes to 0, you have the singularity. The singularity is there, and it's a physical singularity. Everything blows up, and this is going to be a problem in a numerical code. Okay. In addition, you have all sorts of quantities here which go through 0. So the horizon is a badly behaved point as well. And this is also going to be a problem if you want to evolve this numerically. Now you know that you can rewrite the Schwarzschild solution in all sorts of different coordinates where some of these problems can be alleviated. And one set of coordinates is especially useful and relevant for numerical relativity is isotropic coordinates. So if you introduce isotropic coordinates, you make a coordinate transformation where you write your Schwarzschild radial coordinate in terms of this other isotropic radial coordinate in this way. And if you do this, and now you can just work through all the coordinate transformations and look at what happens to the metric, and the metric now becomes like this. Takes this form, okay? And this is attractive for many reasons. One is that you can see that the spatial metric is flat. The spatial metric is not flat. The spatial metric is a flat metric with one overall scale factor. Okay, so this is a flat metric here. This piece is the flat metric, and so this is a manifestation of the fact that the Schwarzschild solution is conformally flat. So the spatial metric can be related to the spatially conformally flat. So the spatial metric can be related to the flat metric just by a scale factor. Okay. And if we want to look at the 3+1 quantities, right? So you've done this 3+1 decomposition, and you've done these conformal decompositions in Thomas's lectures, and so now you can just read off from this what the 3+1 variables are. The lapse is this piece here, because this part is minus alpha squared, so alpha is the lapse is this quantity. You can see there is no shift in here. There's no cross terms in the spatial metric, so the shift is 0. And the spatial metric, as I say, is related to this flat metric by a conformal factor. Okay. All right. And also, the other piece of information, of course, you want in terms of 3+1 variables is the extrinsic curvature. And the extrinsic curvature is essentially related to derivatives of the shift. The shift is 0. There's no time dependence, so the extrinsic curvature is 0. Okay. So this is an especially simple solution. Okay. Okay, so now you've written the metric in this nice form. It's useful to look at these coordinates and see what you've done to your coordinate system. So previously you had a radial coordinate which went from the origin, which was the singularity, out through the horizon at r equals 2m and way out to infinity. You've now made this transformation. If you take a look at what's happened, okay, if you look at what the Schwarzschild radial coordinate is compared to this new isotropic radial coordinate, well, for large r, it certainly goes off to infinity. Right? At very large r, it's clear that this term becomes small, and Schwarzschild r becomes approximated by isotropic r. As you come in, you will find that you reach a minimum here at m over 2. This little r is m over 2. And if you calculate, if you plug the little r as m over 2 into here, you'll find that corresponds to Schwarzschild r, Schwarzschild radial coordinate of 2m. Right? So the horizon r equals 2m is at isotropic r of m over 2. Okay? So the point m over 2 in isotropic r corresponds to the horizon. If you keep going inwards in isotropic r, you'll find that now the Schwarzschild radial coordinate increases again and blows up as you go towards the origin. And you can see here, this r becomes small, this term becomes bigger and bigger, and Schwarzschild r increases again. Right? So now you have a coordinate system which does not include the singularity. Right? In fact, it doesn't include any of the space-time inside the horizon. Okay? Now that doesn't mean that doesn't exist. You haven't done anything to the physics. You've just now chosen a coordinate system in which you only describe the space-time exterior to the black hole. Right? So if you are interested, for some reason, in simulating things that go on inside black holes, I guess because that's the only way to know about them, because you can't look, then this is a really bad coordinate system, because it does not describe the interior of the black hole. Okay? But if you want to avoid nasty things that happen at the singularity, then this is a very nice coordinate system, because the singularity is just not there. Okay? You also, for better or worse, get two copies of the exterior spacetime. Right? R from 2m out to infinity is described here, and it's also described here. So in this coordinate system, you now have two copies, and this is often referred to as a wormhole representation of Schwarzschild, because you now have essentially have an outer copy of one copy of the exterior spacetime, another copy of the exterior spacetime, and they're kind of joined by this wormhole, and there's this throat here at r equals 2m, right? So there are these two copies in this coordinate system. Now, nothing physically has been changed. All right, you haven't actually produced another universe that you can travel through to, or anything crazy like that. You've just taken your solution and represented it in a new way. And so now your coordinates give you 2 copies of the exterior and none of the interior.
How we are avoiding the singularity in this coordinate system?
I've just chosen this radial coordinate such that when I map this to the Schwarzschild radial coordinate, for no values of r, of isotropic r, do I get Schwarzschild r as 0, or Schwarzschild r is less than 2m. It's just a coordinate. I mean, it's by defining a coordinate transformation in this. I mean, I can define any coordinate transformation I like. Right? I can choose to represent this. Within, I mean, I could put anything here and then gone and calculated what the metric looks like in this new coordinate. And it turns out for this choice, it has the pleasant property that I avoid the singularity. Right? I mean, essentially, if I had made any kind of coordinate transformation where this blows up as r goes to 0, then I've avoided this, avoided the singularity. Okay. And this also has the nice property that then I've put this into this explicitly conformally flat form. Okay. All right. Right. The other thing to note about this, so this is just purely talking about the spatial metric. If we look at this time part of the metric, we see that, so this is our lapse, and it's got this particularly funny form. But what we notice is that this lapse here, if we plot it, it will be positive for large r, but at r equals 2m, it will be 0. And it will go through 0 and be negative. So note that the lapse is less than 0 for, whoops. Okay, so in some sense, time, in these coordinates, time goes forward on this part of the exterior space-time up here, and it goes backwards down here, right, in these coordinates. All right. So if we were now to draw a Penrose diagram of this space-time, and I think Sasha introduced Penrose diagrams in his lectures, is that right? So Penrose diagrams are one of these things which are, if you're not used to them, they essentially tell you nothing except they give you a headache. But once you get used to them, you find that they actually are a very, very useful way of representing what's going on in the space-time. Okay. It also takes some time to get used to drawing them, right? But then after a while, you can, always draw a Penrose diagram. Yeah. Yeah, I once heard a story of someone who gave a talk where they presented all sorts of complicated results, and then someone in the audience said, "Oh, that's all very well, but can you draw me a Penrose diagram?" And the guy just went, "Yep," and that was his answer, right? Okay, so anyway, here's the Penrose diagram. So in the Penrose diagram, just to remind you, these lines here represent the horizon, at r equals 2m. This is the singularity at r equals 0. This is spatial infinity here, and this is another copy of spatial infinity over here, which is perfect for our picture because we have two copies of spatial infinity. So this is one end, this is the other end, and because these things represent time-like infinity, this is where, so null infinity, this is where light rays go, okay, or gravitational waves or whatever, okay. So we start with our slice. We can, at t equals 0, we can write the slice as, whoops. This is this line, and so the slice extends, right, from spatial infinity all the way through the horizon. It reaches the horizon, but it does not. It reaches r equals 2m, but it doesn't go to r less than 2m, right? Because this point here is r equals 2m, and then comes through the other side. So this line here exactly represents what we have in this picture, where the slice comes in from r equals 2 from infinity, reaches r equals 2m, and goes back out again, and does not penetrate the horizon. And if we now look at what these slices look like as we go forward in time, then on one half of the space-time, one half of the exterior, one version of the exterior, the slices go forward in time. On the other half, they go backwards in time because alpha is less than 0. So you get slices which do this in time. Okay. So this is alpha is greater than 0 over here, and alpha is less than 0 here. Okay. And so, and again, and the slices do not go into penetrate the horizon. Okay. And so, which particular one of these slices you have depends entirely on your labeling of the time coordinate. So if you, wherever slice you're on, you can relabel the time coordinate and go back to this one. They're all equivalent. Okay, so that's what these slices look like. And you say, okay, now I can surely put this into my numerical code because I have this nice conformally flat data and so on. But, and I don't have any singularity, but the lapse goes through 0. And it turns out that if you take some code up Einstein's equations or whatever form, ADM or BSSN or whatever other funky decomposition you want to use, and you use a negative lapse, then you'll find that it's unstable and bad things happen. So we prefer not to use negative lapse. So alpha okay, in practice, okay? All right. Well, fine. We know that from the 3+1 decomposition that the lapse and the shift are purely gauge. They're purely a coordinate choice. We can choose if we start with our data here, right? We start with this spatial metric. We start with this extrinsic curvature. These are our data. Right? We can now evolve forward in time with any lapse and shift we want. We don't have to pick this annoying one that goes through 0. Right? And you already know, I think from Thomas's lectures, that if you make the trivial choice alpha equals 1, then you'll have geodesic slicing, and the slices will chug forward to the singularity in finite time. Right? So right? And this is the notoriously sophisticated way of calculating pi. Right? Actually, I once ran our code with this slicing to see how accurately I got pi, and I have to say I didn't get very many digits. But yeah, that's how this works. Okay, so we want to choose some slicing that. Actually, I'll draw what happens with these slices just so on the diagram, just to give you some. Right? So if I use geodesic slicing, I start with my initial slice. I've got lapse 1. So everywhere that the slices roll forward like this, and they just keep going forward with a constant time step until bang, they hit the singularity. Okay? So it's a simple. Right? They just all march forward in time and bang the singularity. And of course now they're of course obviously penetrating the horizon now. They move in and hit the singularity. Okay, so we now want to choose a slicing condition, some other lapse which doesn't do that. Okay, so one option is actually to use maximal slicing. Okay, so right? If you choose k is 0 initially, right? If the trace of the extrinsic curvature is extrinsic curvature is 0, so trace is also 0. That's maximal slicing. If you require that you have maximal slicing at all time, then these are, turns out you can show that these are singularity avoiding. Okay, so slices with maximal slices will not hit the singularity. So that sounds good. So requiring maximal slicing, if you go through the ADM equations, you will find that maximal slicing is equivalent to requires that the lapse satisfies this equation. Okay, so if when you start, you say, okay, I'm going to evolve forward in time. What lapse shall I use? Well, as long as your lapse satisfies this equation, then you will maintain maximal slicing. And in fact, at your initial time, alpha equals 1 satisfies this equation, because if you put alpha equals 1 in here, this is, of course, 0. Initially, the extrinsic curvature is 0, so this is 0. So alpha equals 1 satisfies this equation. Right? If you now step forward one step in time, all of these variables will change. The shift won't change. You've chosen not to change the shift. Everything else will change somewhat. You will now have a non-zero extrinsic curvature. This term will become non-zero. In fact, it will clearly be positive. And now you will have to solve this, and you will get a different lapse, which will not be 1 anymore. Okay? And it will turn out that as you go forward in time, what will happen is that the lapse will collapse. There's this standard terminology is there's this collapse of the lapse, and that what will happen is the slices will go up, but they will continue to go up like this, but in this region the lapse will get smaller and smaller, and so these slices will sort of freeze and they will stop, and they won't continue to advance anymore because the lapse in this region is 0. Okay? Okay. What do you also know, what kind of equation is this from your vast experience this week? It's an elliptic equation. All right? So this immediately should ring alarm bells in your head, because if you want to use this to evolve in your code, at every time step you will have to solve this elliptic equation to get the new lapse. Right? And you know that solving an elliptic equation is not fun, and you have to do it every single time step. Now, not only is it not fun to code up solving elliptic equations, it also tends to be inefficient. Right? In a large 3D code, solving a 3D elliptic equation is expensive. It's certainly much more expensive than just doing this sort of this dopey Runge-Kutta stepping forward. Right? Having to stop and solve an elliptic equation takes time. So this is a very expensive way of doing simulations. But you can certainly do this in principle, and you get this. So what happens here, to draw yet another Penrose diagram. Right. What I should really provide is a Penrose diagram stamp, right? And so every time a Penrose diagram comes, you just stamp it on your piece of paper, and then you fill in the details. But eventually you'll be able to throw one of these together in no time, right? This little TIE fighter. Okay, so what happens is that the slices now evolve forward. Well, okay, they don't do quite. They maintain a bit of symmetry. Okay, they go forward just like they were previously, with lapse equal 1, but now it turns out that there is a surface of some r0, some radius, some Schwarzschild radius, which the slices do not go past. They do this surface acts as a barrier to these slices. So what will happen is they will continue to go up, but eventually they will hug this surface, and eventually the slices will go. I mean, after enough time, you can draw this. The slice just goes up, follows this, and then back down again. Okay. So the slices come up and they hug this surface, but they do not reach the singularity. Okay. And so here, clearly, since the slices are now moving forward in time slower and slower, it's clear that the lapse is approaching 0. And in fact, the lapse approaches 0 exponentially in this region. Okay, so
that little surface
Yes, yeah, it's one of the, this is just one of the peculiarities of the Penrose diagram, that this line here represents a constant R surface. Just like this here is R equals 0.
But what R is it? What is the value of R?
Oh, we'll get there, yeah, okay. Later. Oh, I can just tell you. It's 3m over 2. Okay, so it's inside the, well, it's clearly inside the horizon. It's inside 2m, but it's certainly far from, it's far from the singularity, whatever that means. Okay. I was also going to draw the lapse just as a function of time. Yeah. Right, so if your lapse starts at 1, is a perfectly reasonable initial choice for the lapse. You could choose any initial lapse you want, by the way, but 1 seems reasonable. Then over time, what will happen if this is m over 2, I guess? This will start to the lapse will, this is with t increasing, the lapse will collapse. And actually this region in which it's essentially 0 will then grow and actually spread out to fill the whole space-time. Okay. The other thing actually to mention in these slices is that as soon as they start evolving, you now have 2 copies of the horizon in your slice. Right? So there's a horizon here and a horizon here. So you'll actually have 2 points on your data which correspond to R equals 2m. You mean between?
It is not crossing.
In this case versus this case?
Yes.
So here, just because this particular choice of lapse, where it's positive here and negative here, the slices evolve in this way, and essentially because this picture corresponds to this metric. To the metric that's underneath the dust at all times, right? And this is actually a time-independent metric. So at all times, if you look at these, this one, the metric in isotropic coordinates, then at all times the slices does not penetrate the horizon. So this is just writing down the slices for this metric for different values of t. Okay, so you know that the slices don't go through the horizon because you can see it from the isotropic coordinates. And this is just drawing the slices in isotropic coordinates at different times. But the actual metric is time independent. For every slice, you would calculate the metric, and it's the same thing. All right. All right. Continue. Okay. So what is happening here is, so this looks a bit worrying. And if you do a simulation and this quantity falls to 0 and then just starts spreading out, it's like a disease, right? You worry that something funny is happening in your simulation, and indeed something strange is happening. And if we were to plot, let's look at the proper distance from the horizon. Okay, so if I take, this is now Schwarzschild R out here, this is my proper distance and if I have 2m here, this is my horizon. Okay, the initial slice just touches the horizon and there's a copy on either side. So it looks like this, right? It's this picture. This is what R looks like if I were to make this plot. As time goes on, the slices, it's a bit extreme, penetrate the horizon, and I now have 2 copies of the horizon in my data. Okay. Now the slices evolve towards 3m over 2. This is this limiting surface So what happens is these things, they reach the surface, and then they start to, the slice everywhere approaches this surface. So it starts to elongate. And if you calculate now the proper distance between 2 points, okay, so you take two points in your isotropic coordinates, say 2 points, say here and here, and say what is the proper distance between those 2 points? This will keep growing, okay? So the slices, okay, there is right? So these slices stretch, and they continue to stretch. Okay, so the simulation doesn't settle down to any sort of final state. It just would. Well, at this point, things are. If you start looking at metric components and things, they're going to be blowing up here. They're getting bigger and bigger. But if your code can handle that, then these things will actually stretch and stretch indefinitely. Okay, and so this thing asymptotes. People say that this asymptotes to an infinitely long cylinder. If you take this, if you make a surface of resolution around here, then you get this sort of wormhole picture. And as this thing evolves, these things stretch and stretch, and you get this long tube, which just gets longer and longer and longer, and would become infinitely longer. Now, there are many interesting things about this. Well, obviously, there's many interesting features to this kind of evolution. This situation was actually looked at in one of the first papers where people performed numerical simulations of the Schwarzschild spacetime. There's a paper. This was done in a paper from 1973. And in 1973, numerical codes, computers were not as powerful as they are now. And the people who did the simulation, they wrote a code which had 27 grid points. Okay, so this is so few grid points that you could name them all, right? And with this code, with only 27 grid points, they were able to observe all of these complex features, which no one had seen before. No one had seen any of this kind of weirdness before. They managed to capture all of this behavior. And in addition, they then were able to work out an analytic solution to explain exactly what was going on. And so this was really, I think, a remarkable piece of work. And essentially, if you read this paper, which is 4 pages long, not only did they get the solution with their little code and work out what the analytic solution is, they then go on to essentially mention the issues that have to be dealt with to make this better, which are essentially the issues which then everyone spent the next 30 years trying to solve with numerical relativity. So, well, all I have here is this is. Yeah. I will. Yeah. I'm just making you wait. Yeah. All right. So, so this is really a remarkable paper, and as Harold can't wait any longer, the authors are Estabrook et al. From 1973. Okay. If you want the exact journal reference, I can get it, but I guess Google Scholar can probably do the work for you here. Okay. Sorry? Right, this infinitely long cylinder is at a surface of Schwarzschild radius 3m over 2. Yeah. Okay. All right. So, this is all very interesting, but as an approach to doing simulations of black hole spacetimes, it doesn't look like a good idea, because this thing, there's all this strange coordinate stretching that goes on. You don't reach any kind of stationary state. And I mean, this is Schwarzschild, right? It's supposed to be easy. So you don't want all this weird stuff going on, okay? So one way of getting around this, right, is, so one of the issues that came up out of this was that Estabrook and collaborators pointed out was that maximal slicing is a problem, right? This is expensive to do. With 27 grid points, it's not so bad, but in general, maximal slicing is going to be expensive. And then finding alternatives to maximal slicing has been one of the major topics since then. The other thing they pointed out was that using a shift, which is 0, right? They left the shift vector to be 0 the whole time. This was a problem because all of these, this is a non-zero, a carefully chosen non-zero shift could maybe alleviate all this coordinate stretching and stop this going on. So they suggested that, well, if we had some better alternative to maximal slicing and some appropriately chosen shift, then we could do this all much better. What they didn't suggest actually was maybe we actually find some way of doing this where we don't have all this dynamics going on in the first place. So one thing that you can do to solve this problem is you can write down actually the maximal slice, right? So the family of maximal slice. So okay, so here are the maximal slices where the RR, this is the Schwarzschild RR component of the metric. So now everything's back in Schwarzschild coordinates. Okay, so this is a family of maximal slices, which is parameterized by this constant c. Okay, and if we were to choose this c to be 0, then we see we get something quite close to the solution we had before, except that the lapse actually looks a bit will look a bit different. But otherwise, if we set c to 0, then the extrinsic curvature disappears, the shift disappears, and this looks starts to look a lot like the standard Schwarzschild picture. Okay. Now it turns out that if we look at this equation here, or this piece here, because it has a number of roots, and one of the roots is if you choose this root, then you find that then this is a root at, yeah.
Valid that satisfy this particular elliptic equation, right? What do you mean by valid?
Well, I mean that these are slices of the Schwarzschild spacetime, right? And they are maximal. So they satisfy this maximal condition. So I can choose different values of c, and they will all be
in the sense that it satisfies that elliptic.
right. It satisfies this elliptic equation, right? So if you were to actually go through and churn through and calculate this elliptic equation, the terms of this equation, then it would be satisfied. So these are valid maximal slices of Schwarzschild. Okay, and so it turns out that if you choose this value, there's a limiting solution here, which is the one where you have this particular value of c, and for this value of c, you end up with a root at 3m/2, and this actually corresponds to this solution that Estabrook and collaborators found. But if you choose, so you'll find that if we choose this thing, I'll just complete what I was going to say, then alpha is greater than or equal to 0 for r, sorry, not 2m. If you look at this equation and work out what the roots are, you will find one of these. This just turns out to be when Estabrook and collaborators did this work and they produced an analytical solution, they found that this limiting slice that they go to corresponds to this particular solution. Okay? So if you take the solution and you choose these values of r from 3m over 2 outwards, then you'll find that for these values the lapse is greater than or equal to 0. The lapse goes to 0 as r goes to 3m over 2. And gamma rr diverges as 2, and so proper distance okay. So if you take these data, right, they are, plug them into the Einstein equation. If you use maximal slicing, and you use these data, with these choice of data, this choice of metric, extrinsic curvature, shift, and lapse, then these data are stationary. If you evolve, they will not change. If you evolve Einstein's equations with these choices, so they're completely stationary, but they capture exactly this this behavior. And so if you were to use these data, they will represent this region exterior to this limiting surface, but without any of these coordinate dynamics, right? So you've now actually located the shift that Estabrook and co were saying would be very useful, right? This is the shift which stops all of the stretching, it keeps everything stationary. And if we take only this outer part, then we call this a trumpet solution, because this is, in some sense, we've just taken this top half and the picture looks like a trumpet. I'll show that later. And so we can just refer to this as a stationary. Okay. All right. So maybe I should take a break for a few minutes now, as per convention, and then we can go. I can talk about how we. All right, let's continue. So, so this solution that we have. So we see that if we consider the solution for this region from the surface, this limiting surface 3m over 2 out to infinity, then we can write this down as a completely stationary. So stationary data for an evolution. This is a little problematic. This is a bit irritating because it starts at some surface. But we can ask: can we make a coordinate transformation like we made the isotropic coordinate transformation, so that this point here, where we want to start, is actually moved to isotropic r equals 0, and so then we would have data where we can consider the full domain of r equals 0 out to infinity, and that would correspond to this 3m over 2 out to infinity. And then we would be able to represent this full data, and we would have a nice example of a stationary space-time to evolve. Okay. So, yeah. Okay, so what we do is we again let Schwarzschild r be some factor times r, but now this is not the same one as before. We don't know what this is. Okay. Okay. And we know that the Schwarzschild solution is conformally flat. Right? It can always be, if these are all solutions of the Schwarzschild space-time. Right? I mean, you thought that the Schwarzschild solution was a stationary black hole, nothing happened, and now you see all this crazy dynamics going on. This is all coordinate dynamics. This is all changes in the coordinate system, and the physics is exactly the same. This is just this poor old black hole sitting there doing nothing, but the coordinates are all changing around. So it's still Schwarzschild, it's still conformally flat, so we know that we can write it in this conformally flat form. And we, of course, have maximal slicing because we've chosen maximal slices. And we also know, it turns out, I guess probably Thomas did this, that the transformation of the trace-free part of the extrinsic curvature to its conformal counterpart is is like this. There is this transformation. And so if you work through this, you will find that this quantity, this contraction of Kij, Kij, this of course is the same as Aij, Aij, because there is no trace K. And this is, I think 6. Is this for this solution. So if you work this out, if you just take this and you churn through the calculation, you will find that you get this. Now, if you make there's this nice result that if you now make this isotropic coordinate transformation, even without knowing what the conformal factor is, it turns out that when you transform this, all of the conformal factors cancel out, and we also have that Aij okay, and so you get the same result for the conformal quantities, but now it's the isotropic, it's quasi-isotropic R instead of Schwarzschild R. Okay, and so now if we want to solve the to get this, so all that's missing here is the conformal factor. If we knew the conformal factor, we could translate between the Aij that we already know about in Schwarzschild coordinates to our conformal Aij, and of course we would be able to construct our metric, and we would be done. So all we need is the conformal factor to make this transformation happen. And so to do that, we have to solve the Hamiltonian constraint. So if we write down the Hamiltonian constraint, we get the following. Right, the piece that's in here is, this is the Hamiltonian constraint. We know what this is, just worked it out. So this is all right, and we choose c squared to be from this this thing here, and we get 27 square that thing. So for our particular trumpet slice of Schwarzschild, we make this choice of C, and then we solve the Hamiltonian constraint. Okay. So once again, we have a nice little elliptic problem, elliptic equation. This is spherically symmetric. It's Schwarzschild. So this is a one-dimensional elliptic equation. It's got a side of the -7 here. It's nonlinear. This is an odd power, just like the problem that I was supposed to show you yesterday. And so this has unique solutions, turns out. And so you can go about solving it with the techniques that we've already talked about. Okay. Now, one thing, though, one problem you're going to have, of course, is you say, well, this conformal factor, right? In the Schwarzschild case, this blows up at r equals 0. And essentially, if you have a black hole in there, the conformal factor has to blow up. That's where you've captured the fact that there's a horizon and so on, right? Because the real physical metric is the conformal factor to the power 4 times this flat spatial metric. If the conformal factor was some innocuous function that sort of wobbled around a bit and then went to a constant r equals 0, then you would clearly, your physical metric would not be doing anything very extreme, and you wouldn't have a black hole. So this thing must be problematic. But what you can do is you can factor out the divergent behavior and solve for only solve an equation for only a regular function. Okay, so let's look at So in some ways, the history of numerical relativity, I guess as with all science, is completely backwards and mixed up and confused. And so the technique that I'm going to use here was actually originally used, motivated for solving binary black hole data. So although you would think that the simple Schwarzschild case should come first, actually the trick comes from doing binaries. But nonetheless, here we go. So let's look at the solution near r goes to 0, or as r goes to 0. Let's let the conformal factor go as r to the n, to some n, right? So the Laplacian, as in our previous discussions of these equations, this is going to go as r to the n minus 2. If we look at our source term here, right? This goes as, the 1/8 doesn't go as anything very interesting. Side of the, I don't know, something over, I won't say k, I'll just put this as over the 6th, right? So if psi goes as n, right, then we have r to the minus 7n times r to the minus 6, okay, and so this goes as r to the minus 7n minus 6. So for this to be consistent, right, for consistency, right, we need that n minus 2 must equal minus 7n minus 6, and if you solve that, you find this gives you n equals negative 1/2. Okay, and so the conformal factor goes as 1 over r to the half. Okay, and this looks very encouraging. Well, we know it looks encouraging. I mean, this is the right answer, so of course it's encouraging. But if you just take a look at this, see, this is very nice because in the wormhole case, this thing blew up as 1 over r. We don't want a wormhole anymore. We want this other funny cylindrical end. So if it came out as 1 over r, we would be unhappy because we would have a wormhole again. But if it came out as something that did not diverge, we would also be unhappy because this would be hard to convince ourselves it was a black hole. So we get something else. We get something that diverges, but it diverges at a different power. It diverges as 1 over square root of r. Okay, so we have a black hole solution, but it doesn't look like the wormhole before. Okay. Now we know actually exactly what this is. Okay, because we want our isotropic radial coordinate to go to this limiting surface. We want r equals 0 to correspond to Schwarzschild r is 3m over 2. Okay, so to have we need r right? So as r goes to, right? So if we now say psi is square root of r, we can now equate these, right? If we put this in here, we get psi squared is k squared over r. You multiply by r, the r's cancel out. So k squared must be 3m over 2. Right? This must be the limiting behavior of the conformal factor. And so this is now completely consistent. The fact that this thing blows up as 1 over the square root of r gives us exactly the behavior that we want, that the Schwarzschild radial coordinate limit reaches a limit of 3m over 2 as we go to the origin. So this is exactly the solution that we want. Okay. We also know, if we want to solve this equation, that this is Schwarzschild, and that far away the conformal factor must fall off as 1 over r. It must approach 1, right, because it's got to look like ordinary flat space far away. And the deviation from 1 must fall off as 1 over r, and the coefficient to the 1 over r should give us the mass of the black hole. So far away, it should look just like the 1 minus 2m over r that we had for standard isotropic coordinates. So far away, meaning that goes to infinity, okay, and then we can have corrections, of course, at higher orders, but the leading behavior should be this, and so this will give us the correct mass of the space-time. I actually haven't talked about how you get the mass out of this, which I will do that tomorrow, but you're going to believe me anyway because you are going to guess m as the mass. But if we actually do a calculation and calculate the ADM energy of the space-time, then indeed this is the mass. So we want this form at large radii. Okay, so now we have a we know that we have captured, and we can also prove, actually, if you want to check, you can also prove that the next term near the origin does not diverge. Okay, so the next term after this 1 over r to the half term is going to be regular. It's going to go to 0. So we now can construct an ansatz for the conformal factor where the asymptotic behavior at r to infinity is already taken care of. The divergent behavior near r equals 0 is taken care of, and all we need to do is solve an equation for everything in between to get a legitimate solution. All right, so now, right. So we choose so there's got to be some correction function that we're going to solve for, and then the rest, which is this, we want to include all these pieces we have, but we don't want them to affect each other, right? So we want this 1 over square root of r. We can't just use this as an ansatz because this falls off too slowly at infinity, right? So we have our behavior near the origin, and then we conveniently kill this off at large r, right? So we just put in this this factor here, right? And we could choose any number of functions here. This is just something which goes to 1 as r goes to 0, right? And goes to 0 as r goes to infinity. And it falls off fast enough that it's not going to interfere with our other term. And near infinity, we want 1 plus m over 2r. And we want this term to be dominate at large r, but we do not want to be dominated we don't want this term to affect anything here because we don't want a 1 over r blow up. So we just put some factor here, which I just made up, right? And this goes to 0 as r goes to 0, right? And it goes quickly, right, to 0, right? Quickly enough to 0 to kill off this term. And it goes to 1 as r goes to infinity. Okay, so I've now blended together these two functions so that this piece here captures the correct behavior at the two ends.
That would be 1 plus m by 2r.
Sorry?
Far away. What
Yeah? Oh, yep. Sorry. Thanks. All right. Okay. And so if I can now plug all this into the Hamiltonian constraint, and I can solve for this function here, which turns out to be quite regular and well behaved. Okay. And that's sort of the last of the lab exercises. And I'm not sure if everyone will get to that exercise, and I'm not sure if anyone will actually manage to solve it. There's all you can imagine, because you have to calculate the Laplacian of this thing, right, which is not 0, and include this in your source term. And so there's all sorts of nasty details, but in principle it's the same kind of problem, nonlinear problem you've looked at before. Okay, so I have some time. All right. Right. So now we could ask a different question, which is, let's imagine that we actually start from data that are, so to wrap this up, once we've done this, we've now produced data which is in this trumpet form, and they are time independent if we evolve with this particular lapse and shift that we have from the solution, and they cover this entire isotropic radial coordinate. So we can just put this data naively onto some computational domain and evolve them, and now we have a lapse which is greater than 0 everywhere. Okay, we do not go anywhere near the horizon, and we have actually a stationary solution. So this provides an excellent test case for a code, because you put these once you've constructed all this data, you put all the data in and you run it, and you should get a very boring answer, and that nothing happens. There's no interest, no dynamics. Okay. Okay. So it turns out that historically, when people did binary black hole, did black hole simulations, people tended to start with this wormhole data, right? So they started with the conformal factor 1 plus m over 2r, and the flat metric and the 0 extrinsic curvature, and they said, okay, now we're going to maybe we start with lapse equal 1 and shift equal 0. We choose some clever lapse condition, probably not maximal slicing because it's expensive, but maybe we're tough and we'll just do it. And we choose some clever shifts condition, and people spent 30 years developing all manner of clever shift conditions. And you say, okay, can I evolve that data? Can I make it evolve so that it goes towards actually this solution? Okay? And it turns out that you can. And the thing that does this for you is the shift condition, if you choose it appropriately. And it turns out that historically the appropriate shift condition was used completely by accident. None of this was by design, but in retrospect we can pretend. So if you take you get out your Penrose diagram stamp, and you consider what I'm wanting to do is I say, okay, I take my maximal slices, and I now say, instead of having these things stretch around this R naught and get longer and longer into all this stuff, I really want to introduce a shift so that I just get the time independent part, the stationary part. So I essentially want to use a shift. Right. Okay, we're now, and I start with this slice, and then the first slice somehow starts to detach from this end, and as time goes on, they end up approaching this slice, but not extending all the way to the other end and not stretching. Right? Now you say, well, how do you do it? Is there a shift that will do that? Well, there's a shift that will do pretty much anything for you. Okay, you can certainly, in principle, you can construct a shift that does this, and there is actually a shift condition that people use, which for which this happens. And I have some pictures here that I can show you. Make this work. So what the shift is doing is moving the points here. These are the other asymptotically flat end, okay, at r equals, the other r equals infinity, okay, and because you don't have a point at r equals infinity, you've taken your grid and you've divided it up, so you have some very, some smallest value of Schwarzschild r, and that corresponds, to isotropic r, and that corresponds to the very largest value of Schwarzschild r, and that point you want to give that some, horrendous shift, which moves, which essentially, the shift is labeling where the points are, so the points don't move, right? They sit on your grid, they're not going anywhere. Right? The computer doesn't sort of trundle along the room, right? The points are fixed, but their labeling in terms of the Schwarzschild coordinates can change based on the shift. So the shift relabels the points, if you want to use less dramatic language, over to this location, okay? Now, can I make things happen with the projector? What's happened here is we have.
Where's the pointer? The line, the table, this line.
Oh, you mean the? Well, okay. I'm right here, so it's okay. So what we take is we've actually taken a very small number of points. It's just these few points here. So this dark line is the initial slice. So here you see we've plotted the Schwarzschild radial coordinate, and this is the proper distance from the horizon at r equals 2m. And so you have your two copies of the exterior space-time, and we've just taken 6 points on a numerical grid and plotted what they are, and then we start to evolve, and we use this particular shift condition that we have that does this trick, and you see that what happens is that these points, as I say, they are not going anywhere. They're the same locations in isotropic R, but their labeling in terms of Schwarzschild R changes. And these points here, this point in particular, right, you can see it moving in very quickly to this one here. And this surface here is our cylindrical surface. So these points rapidly move in into here and get relabeled. I mean, there's some small relabeling that goes on out here, but not nearly as dramatic, right? So this point starts at r equals, and this is the times t is 0, 1, 2, 3 m of evolution. So it starts at almost 10 m and moves rapidly in and just a few m to this point here. Okay, so now I can, and if I write it, I can just show the picture in a different way, where I actually plot it in terms of isotropic radial coordinate. So you see all of these points that I've shown, they are in the same. It's not so clear. You can see for these ones, they're the same isotropic radial coordinate points, the same grid points. It's just that their labeling in the space-time has been changed. So these points, which are way up here, they come rapidly down and they end up at this the surface. I should say I've used it. We haven't used maximal slicing here. We've used maximal slicing as a pain. It's an elliptic equation. We've used a similar kind of equation with similar properties, but an evolution equation. And for that, the limiting surface is a slightly different location, but it's the same essential behavior. And so what happens is if you draw an embedding diagram, this is your initial data, which is this wormhole picture I drew before. I'm only showing you these very nice pictures that Frank Omer made for a paper we wrote. And then this turns then into this trumpet picture. And if you look actually at what's happening to these points, if I take the points that are the closest to the origin, so I did a simulation which had extremely high resolution just to illustrate this. These points are at a these are the 3 points closest to the origin in isotropic coordinates. If you calculate in the initial data what Schwarzschild coordinate this corresponds to, it's these values here. So this innermost point, this point that's closest to the origin, this starts out at about 2000 m, right? Which is, this is getting you a reasonable distance towards infinity, right? This is very far out in Schwarzschild coordinates. And as it evolves, in only 3m, well, you can see the time here, in only 3m of evolution, this point has raced in towards the limiting surface, okay? And then you might think, well, how can the shift do this? This is faster than light travel or something, right? What's going on? But this is purely a coordinate effect. The coordinates can change at any pace you want. There's no, speed of light doesn't matter. They're just coordinates. And this is really just a relabeling of the coordinates. So it's not that this point is, something's moved, it's just that this point has been very rapidly relabeled from being at 2000 m all the way down to this limiting surface at actually in this case close to 1m. So there's this very rapid movement of the points. If we look at a Penrose diagram, we see much like what we had before. This is an early time behavior in the code. You can see that I've got the time here. It goes only as far as 8m of evolution. And we start with our slice here, and as we move up in time, the grid points start getting thrown over into this region here. Because we're not using maximal slicing, then this limiting surface is not actually a barrier, and the points pass through. But that's I'll say a little bit about that probably next time. If we look at the late time behavior, what we can do is, see, now these things all end up kind of up in this corner, but we can relabel the time, right? We can just relabel our time coordinate, and if we do that for the late time behavior, we end up with this picture. So this is very late. This is now starting at 30m of evolution up to 50m with a relabeling of the time, and the line, the solid line you can see under the points, this is the analytic solution. So if you take this analytic trumpet solution, which for this particular slicing equation condition is a bit different to the one I showed you, but it's again has similar properties, you can work that out, and then you see the data lie exactly on top of this analytic solution. So this thing evolves very quickly towards analytic solution. One other interesting property of this, which I think is worth mentioning, if there's a lot of rich geometry that's going on here, and you can ask yourself all sorts of, you can test your intuition about GR with these things in many ways, and you usually find your intuition is wrong, and then you learn something. So one great thing you might ask is, say, well, once these points have gone in here, they're now, they're close to the singularity. Presumably, that whatever you do to them, they're not going to move back out again, right? Because you would think that in order to move back out, you would need some negative lapse for them to come back out. But in fact, they can move further out, because what the shift is doing, right, if you take lines of constant Schwarzschild radius, these points here, they're not, if they were to come back out this way, you would need the lapse to be negative. But the shift is pushing them across here, and so the shift is actually moving this point from this radius, Schwarzschild radius, radial coordinate, to this Schwarzschild radial coordinate, which is further out. So by sliding the points across, you end up actually moving the points out to larger Schwarzschild radius. So if you have so your intuition about what the points are actually able to do can be difficult to build up this intuition, because the shift can have an interesting effect. And I think that's all I wanted to say about what happens in these simulations. Next time I'll say something. I didn't say anything about the slicing condition that we use here, and I'll just mention that very briefly next time, because there's some interesting points about that. And then I'll move on to how we produce binary initial, or one way to produce binary initial data. Right. Thank you.